Hello friends, welcome to part 9 of our series, and just to share a good news, we are almost done with our analysis and soon we are going to do the data modeling, and then we will focus on applying some machine learning algorithm. Now before going to that, what we are going to do is apply log transformation, because we know that some of our numerical features are skewed, so we want to handle that first. So just by writing these 2 lines of code, what we're doing is we're taking all the numerical features including the sale price, and we're just running a log transformation on top of it. Okay, so there's the first basic step we will do, and in the next step what we're going to do is use one-hot encoding to convert our categorical features into numerical features. Just keep in mind that our number of columns in the data set will increase because of that. Alright, so before we apply our one-hot encoding method using the inbuilt pandas inbuilt getDummies method, what we are going to do is do some data separation. So we are going to assign the sale price, which is our target variable, into a variable called y, a standard process, and we are going to drop the sale price from the training data because we are just putting the features in one data frame, and we are also dropping the ID column, which is no longer required for us. Okay, so by doing this we are creating a model data, which on top of it we are going to apply some regularization method, so that, because remember after doing one-hot encoding, we are going to generate too many columns. So just by doing regularization, what we mean to do is reduce the number of features which are not important. So if we run this, great, so now we have all our training data in this model underscore data along with the features, and what we can do is we can see a number of columns we have. So just by doing this, oops, my bad. Oh, okay, so I have probably already run this command here, so I can just comment that out. Okay, I'm also going to do this here and do this here. So if I just now run it, great. So of course it's 263 columns. Remember we started with only 81 columns, but now because of the one-hot encoding and few of our own feature engineering, we have got to somewhere around 263 columns. So let's see how we can reduce it. Okay, so as we know, a standard practice is we have to keep a certain amount of data to be used as a validation, right? So what we're going to do is we have 2 files, right? One is the training data set we have seen, and we have a separate test data. So for the time being, what we're going to do is we're going to split our training data itself into 2 parts, one for training and one for testing, and then we'll have a separate test data set which we haven't touched it yet, that we can use as a validation set, right? So that to make sure that we have not used the entire data for training. And then what will happen is, if we do that and if we use the entire data set for our training, we will run into a problem called overfitting, right? So that's what we want to avoid on the first place. So let's see, we are splitting this data, the training data I should say, and what we are doing is 70% we are keeping for training, and 0.3 part, 30% we are keeping for testing. Keep this in mind, this is only the training data. Okay, we haven't touched yet the test data set that we got from the Kaggle project. Okay, let's see what happens when we run this. Great, so we have for training data, we had around 1400 some records. So here we have broken it for into 1019 records for training and 437 for testing, and similarly happens for the sale price as well. Okay, but here it will be blank, the reason being that's what we have to predict. Okay, next step before we can do the data modeling is first we will using the sklearn's preprocessing module. We have 2 interesting tool. We have robust scaler and standard scaler. What we are going to do is we are going to standardize our numerical features, which means that the means of those features will be at 0 with a standard deviation of 1. Okay, so Why do we do that? Because this helps in efficiently learn the weights or coefficients of the mathematical equation, underlying mathematical function, right? Now just keep in mind that we are doing this only for the numerical features and not the dummy features. Okay, let's run this and see. This is a standard pre-processing technique. Okay, I think I missed something. Okay, yeah, it says sales price and ID not in index. Let's see how to handle this. Alright, so what I've observed is you remember we have created a list of all the numerical features, but while dropping these columns I didn't realize that in that list, so numerical underscore features is a list, Python list, and I should have removed the dot ID and the dot sale price, and because of this it threw that error earlier. Okay, all right, so next we are initializing a standard scalar, and for the X train and the X test we are basically using the fit transform method. It's a standard, you can Google this line of code, and it's a pretty much common code for doing a standard scalar operation. And what it is going to do is it is going to transform all my numerical features with a mean 0 and standard deviation of 1. Okay, so in every machine learning project basically we will have one or the other error function or loss function, or we call cost function, to make sure that whatever we are modeling or predicting, it has to be minimized as much as possible. Even in this project it's no exception, and Kaggle computation has prescribed to use RMSE root square mean error as the standard cost function for everybody. So we're going to define as a function there. Okay, I'm not going to explain too much of the code here because this is pretty standard, and there are lots of documentation on this one, and we're also using the cross validation score, right? These are pretty common concepts in machine learning, and I encourage you to go over it, understand this, how to write the syntax. Basically concepts wise, we are just taking a set of data, holding it as a test, and then for the remaining one we are using as a training data, and based on that we are using a cross validation, right? And in order to because remember we have 263 columns, so what we want to do is depending on the importance of those columns, we basically want to reduce the number of features, and my favorite is lasso. Again, this is a pretty straightforward code. We are using the grid search cross validation in this case. What you can do is go over this code line by line, and this is pretty straightforward standard way to implement a lasso regression. And what it will give us is basically it will help us drop the columns which are not significant for us. And if we run this code, what we are going to see is that the training RSME is 0.00122 and the test RSME is 0.00125. So what does it mean? It means that the error while learning the training, using the training data, and while using the validation data, the error is more or less very similar. So what does it mean? This means that if the training error and the test error are pretty close to each other, that means this is actually means we are overfitting. That means we're trying to basically memorize the entire data set, which is a bad thing for doing data analysis, because in data analysis the objective is to find a general pattern, right? Of course we want to minimize the test error, but then if training error and test error are almost equal, as we can see here, that means it has just memorized it and it has actually not understood the pattern. So what we're going to do is we're going to use the lasso method to drop the features which are not important, and as a result we can improve on our overfitting. So if we're again, the standard piece of code, no complex theory here. If we plot this graph, what you can see is, and it actually holds true with our intuition, that whenever the size of the house is big, the sale price is high, the overall quality is good, the sale price has a linear relationship. Year, how old is the building, is equally important. Total square feet of the house is, remember, which is one of the feature we have calculated. Lot area, garage cars. That means based on the general intuition that we have about a property, lasso regression also validates our thought on this one. And we can see in the descending order which are the columns which are not very influential for us, right? So the top, we can take the top 5 or top 10 features from the lasso regression, but you can see here almost 232 features were dropped because it did not find any good major relationship with the sale price. So that's what lasso regression does. You can similarly also do ridge regression, and also you can try it without doing any kind of regularization as well. That I leave up to you for practice. Alright, so finally we come to a point where we can use actually the machine learning libraries. So we know that over experience that XGBoost library is kind of one of the state-of-the-art machine learning library nowadays. So what we're going to do is quickly import the library XGBoost, and we are going to set the standard parameters there. And what we are going to do is pass the xtrain in order to learn from it, and we are going to pass the label which we have already just created. And this number of features which are important for us comes from the lasso regressions. If you see here, this got the columns that are important for us, okay, so which is nothing but 263 minus 232 features. So you can also experiment with the number of features. You can start with probably 10 of them and see whether there is any improvement in the performance and so on. So what happens when we learn run this script, it is basically going to learn using the training data, and because it's a supervised learning, so it needs a label as well. So what happened here is it did the learning. Now next, see what is the performance of this script here. So it has run properly, and just by running, I've already ran this. Let me run it again. And previously, what happened was we complicated the RMSE root mean squared error definition. It is actually in a simpler term. That means what is the difference, sum of the square between the difference of the actual value minus the predicted value. And predicted value is something we are going to calculate given we provide the test data, right? Test features, and we are going to predict the the label, the sale price, right? So just let's run this script, and what we get is a very small error which is 0.004. That means we have actually, because of all this data analysis, we were able to actually score a very good value, and this could be a very good model for predicting your sale price. Now what you can do, you can of course plot the prediction values, and you can see what is the sale price of the features that we want to predict. Great. So this is all we had to discuss in this housing price prediction. Feel free to try with other libraries, see whether you can improve this performance, whether you can also try to apply random forest, you can try to apply ensemble methods. Of course XGBoost takes care of that, or you can also try deep learning if you are interested, or use neural networks. It's totally up to you, but then the primary part of exploratory data analysis remains more or less the same. Okay, with that, I wish you all the best in your learning with and doing data science. Make sure you keep practicing, keep updated about all the latest libraries that are available, because every day we are making improvement. So, and XGBoost is one of the examples where actually we have engineered this library and made it more efficient until lately. So keep practicing, and if you should have any questions or suggestions, please do put it in the comment section, and if you want tutorials in other areas, please do let us know. So have a great day.